Hello all, welcome to the channel Way to Electronics. This video is about common emitter configuration. In my last video, I have explained common base configuration, and this is a continuation for this BJT configuration. Common emitter means the emitter terminal is common to both input and output. In this case, it is common to both the base and the collector terminal, and this is a most frequently encountered transistor configuration, and this is a structure for both NPN type and PNP type where the emitter terminal is common. The emitter, base and collector currents are shown in their actual conventional current direction. Even though the transistor configuration has changed, the current relations developed earlier for the common base configuration are still applicable. And proper DC biasing should be applied for both the type of the transistor in order to get a proper regions of operation for the amplification application. In order to describe fully the behavior of the common emitter configuration, we have to consider two sets of characteristics again in this common emitter configuration also, that is one for input or a base emitter circuit and one for output or collector emitter circuit. And for this common emitter configuration, the output characteristics are going to plot for the output IC versus the output voltage VCE, and for the ranges of the input current IB in both the transistor, and input characteristics or plot of a input current, that is IB, and versus with the input voltage VBE for a range of various values for the VCE. Now we shall see the input characteristics of this PNP transistor in the common emitter configuration. Here the input characteristics are plot for the value of IB versus the input voltage VBE for the various values of VCE. As we see here, the curve of IB are not as horizontal as those obtained for IE in the common base configuration. This indicates that collector to the emitter voltage will always influence the magnitude of the collector current. Next we shall see the output characteristics. Here also again we are defining the output characteristics for the three regions of operation, that is active, saturation region and the cutoff region. First we shall see the active region of operation for this common emitter configuration. Here the active region, which is a portion of upright quadrant that has a greatest linearity, that is the region in which the curves of IB are nearly straight or equally spaced. So that particular region we call it as an active region. This region exists to the right of the vertically dashed line at VCE sat and above the curve for IB, which is equal to 0. That is about the active region. Next region of operation is saturation region. Here the region which is going to consider to the left of this VCE sat, which is called as a saturation region. So in the active region of this common emitter amplifier, the EBJ is always forward biased, whereas the CBJ, that is collector base junction, is reverse biased. And this active region of common emitter configuration can be employed for voltage, current or power amplification. Next we shall consider this cutoff region for this common emitter configuration. Here the cutoff region for this configuration is not as well defined as for the common base configuration. In this configuration, IC is not equal to 0 when IB is 0. The reason for this difference in collector characteristics can be derived from this equation, that is IC, which is equal to alpha IE plus IC BO. That is, we know that the collector current which is having a two components, one is minority component and majority components. Here this alpha IE is replaced with the IC plus IB, that is the emitter current which is always equal to the collector current and the base current. And at the condition when IB equals to 0 microamps, we are going to get this equation, that is IC which is equal to alpha IB by 1 minus alpha plus IC BO divided by 1 minus alpha, and this will be obtained by the equation ICO which is equal to ICBO divided by 1 minus alpha. As I told, this will be obtained at a condition when IB equals to 0 microamps. Next we are going to define beta as we defined alpha in the common base configuration. Beta is going to define in two modes, DC mode and the AC mode. Now we shall see the beta which is going to define in the DC mode. In this DC mode, the levels of IC and IB are related by a quantity which is called beta. So beta DC which is equal to IC over IB, where this IC and IB are determined at a particular operating point on the characteristics. For a practical devices, the level of this beta which is going to consider about 50 to 400, with most in the mid range. As for alpha, the parameter, this beta reveals the relative magnitude of one current with respect to other. For example, for a device with beta value which is having 200, it is nothing but the collector current IC is 200 times the magnitude of the base current. Next, we are going to define this beta in the AC mode. For AC situation, an AC beta is defined as beta AC which is equal to delta IC divided by delta IB at VCE is constant, that is change in the collector current to the change in the base current. And this formal name for this beta AC is a common emitter or a forward current amplification factor. Next we shall see the relationship between alpha and beta. IB is given as IC over beta, and whereas IE which is given as IC over alpha, and we know that emitter current which is equal to collector current plus beta. We are going to substitute these values so that we are going to obtain the alpha as beta divided by beta plus 1 and beta as alpha divided by 1 over minus alpha. So we are going to substitute the same values of this, and so that we are going to obtain in the IC value as IE which is equal to beta plus 1 into IB. Thank you.